Welcome to this lesson, Introduction to Blockchain, presented by Coding Bootcamps. In this lesson, we're going to talk about the operation of a blockchain and mining on a blockchain. And this is just a little more about the instructor. We have covered this information. So what we learned so far is a bit of the history of a blockchain and the overall architecture. We also talked about some Bitcoin and gave an introduction to the blockchain types, public and private blockchains. And we talked about hashes on the blockchain. So now let's take a look at some of the blockchain operations and mining procedures. So once data is entered into the blockchain, it is permanent. So that is one of the key reasons why blockchains are useful, is the entire blockchain is permanent and cannot be changed. Written data is hashed and cannot be changed. So we saw an example that hashes are very sensitive to changes. So maybe we should say that the hashes make the changes known or make them obvious. So if something does change, we can overwrite it with the correct information that before any type of change was attempted. And blockchain nodes must synchronize all together in order to come to consensus. Because the idea is that every node has the exact same data, and it wouldn't really be useful if there was different data on different nodes, because overall the entire network is supposed to have a single ledger. So blockchain operating procedures and terms. So one term we're going to hear a little bit about is a term called a nonce. And a nonce is a number used in cryptography, and it's a number. It's never used. It's only ever used once. And a nonce is often a random number, and it can include a timestamp. And a nonce prevents repetition of patterns. So that's one of the one thing that the nonce does for us is it prevents any kind of repetition. So if anybody had thought that they could go in and cause difficulties on the blockchain by looking at patterns, the nonce is there to prevent any kind of patterns. And finding the block's nonce is a key requirement for adding a new block to the blockchain. So you can see here the client, and you can see the client request and server response. A nonce is requested, a nonce is then sent, and you can see here the username, the nonce, and the hash, and the nonce and password, and then a token is returned. So we can see here some of the ways that the nonce is actually used. So a Merkle tree is actually the Merkle tree is discussed quite a bit in the white paper we saw from Satoshi Nakamoto about the blockchain. So our Merkle tree is essentially a tree structure of hashes. So it's hashes of hashes, essentially. Every leaf is labeled with the hash of a data block, and every non-leaf is labeled with the hash of the labels of its child nodes. So we'll take a look at this in a second, but Merkle trees are used for data verification, and they are also done for searching purposes. Merkle trees are very fast data structures, and data is transferred between computers in a peer-to-peer computer network, and Merkle trees are used for that data verification. So we can see here the actual Merkle tree. I guess it looks like a kind of an upside down tree, but here you can see what it was talking about here. These are the leaves here, so these are the data blocks, and then the non-leaves actually have the hashes on them. And you can see that these hashes are pointing back to previous blocks. So as the blocks go up, you can see their pointers. So they are hashes of hashes. And Merkle trees are also used for data compression on the blockchain. And let's talk a little bit about a block. So we introduced this a little earlier, but a block is a file. If you could ever navigate into the node where the blockchain is running, you could actually find the blocks are highly, highly encrypted, but you could actually see the block files there. I wouldn't recommend trying it, but a block again is a file, usually limited to about 1 MB, and that for the most part is true across the board. Imagine there could be exceptions to that. But again, we can think of it as a block as a cell of a spreadsheet. So the overall spreadsheet could be the blockchain, and each block could and each cell could be a block, and data is written into the cell. It also includes things like timestamping, links back to the previous block. Block structure has 4 elements. So we have the block size, the header, and some other transaction information. So we can see here the description of block structure. So we can see here there are fields called the magic number, block size, the block header, and there's certain information in the block header, the transactions, and the transaction counts. So and one of the things that goes on while blocks are being validated is the miners are all checking for the correct block size, the number of transactions, the transactions themselves. We make sure that the block actually matches the expected structure. We just don't look at the transactions. And so some of the terms that you may hear, a block height is just simply the number of blocks. And I think we saw that on the Blockchain Explorer. We saw actual block height discussed, or maybe it talked about, I think it might have just said height. The block time is the time needed to generate the next block. So forks, interestingly, we're going to see an example of a fork. There are temporary forks in a blockchain, and we'll see an example of that. But there's also something called a hard fork. A hard fork is when, in our blockchain community, if some of the community moves off and decides to go a different direction, they create what's called a hard fork, meaning we're going to take that last part of the blockchain that we all agree upon, and then we're going to make a full copy of that. And then we're going to use that as essentially a new blockchain, and we're going to move forward with the updating the application in a different way and adding data in a different way. And there are examples of hard forks. If you look for Bitcoin Cash, and there are some other examples, you can look up hard forks. It just means that there's been a split in the community. And a temporary fork is just simply we're all waiting. We all create kind of a temporary block on all the miners create a temporary block on their nodes, waiting to see if they are going to be the one selected to validate the transactions. And mining again. So there are lots of ways to define miners. Generally, miners are thought of as those that operate the nodes, those that keep the blockchain network updated and organized. And I agree with that definition. Miners verify and group transactions into a block. And miners also take part in the consensus algorithm to keep the ledger synchronized. So they will all vote on the transactions and validate that they are up to date. And then that one single new block is relayed to the entire blockchain, so everybody has the exact same data or the exact same copy of the ledger. And then when transacting and actually pending transactions are created. So we'll actually see this as transactions come in before they're validated, they are considered to be pending. And miners receive a notice of pending transactions and then begin to verify them. So verifying the transactions is essentially the work done to add a new block. So the miners verify the records, they add transactions to the block, and then as soon as all of the transactions are added, they begin to look for the new nonce for this new block. And then the hash will be added. So the miners use the computing processing power to find that nonce, and this is called the proof of work. So completing the proof of work essentially proves that the miner is contributing transaction, validating, and providing computing power and electricity to the blockchain network. At a certain interval, all processing on the blockchain stops, and this is done for broadcasting the new block across the network. And when 50% of the nodes agree, the nodes synchronize. So if I win the proof of work, I broadcast my validated transactions in my new block. If 50% of the miners agree, the new block is added. I receive an award, and then the whole process begins again. A little bit more about mining. Locating the nonce while running the proof of work involves really no special skill set at all. Proof of work is the software uses a random number generation to simply test for the nonce. So it would be exactly similar to if you had a combination lock and trying different combinations until you opened it. That's exactly what's going on. So we can see here is our temporary fork. So as the proof of work is running, miners work to find the nonce for the blocks. So we can see here are our 3 permanent blocks in the blockchain, and we know there's going to be a block 4. So every node gets 4A, 4B, and so on. And so the miners begin to add and validate the pending transactions. And as soon as the proof of work is done, I can relay my information. If I win the proof of work, say I'm working on 4A, the 4A will just become the new block 4, and then all of these are just discarded. So for an exercise, what would happen if the ledgers of the nodes did not reach consensus? What would that look like? Think about that. Would that be useful? And a little summary. So our blockchain elements. So we had our nonce, our Merkle tree, our block data and terms. We talked about block height, block time, procedures, other terms. And please do go through this assessment. Again, true or false, a nonce is a random number. Add it to the block hash. True or false, a Merkle tree is not a way to search and compress data. So please take a look at the assessment. And just like we talked about before, the correct answers are in the previous lesson we just completed. And again, for additional resources, please consult your learning materials. And for additional training, please also consult your learning materials. And in our next session, we're going to talk about blockchain cryptography. Thank you.